This week represents the first of 2 weeks that we will spend on nuclear chemistry. This is also the last two lectures for the chemistry class. We will have our last discussion together May the 7th, and I am thinking about giving an in-class final examination on May the 14th. I may or may not give that test in class. If I don't, I will need to have all the tests back to me by that time so that I can have all the grades done before graduation the next Saturday. Nuclear chemistry is the chemistry that looks at and studies equations and reactions that involve the nuclei of various particles. This is in contradistinction to the reactions and interactions that occur because of electron transfer and so forth. So nuclear chemistry is the study of reactions that involve charges in the nuclear structure itself. A nuclide is a single type of nucleus that undergoes or is happening in a nuclear reaction. And a nucleon is either a proton or a neutron. So when we talk or use the term nucleon, we're talking about a collective term that takes into account all the protons and all the neutrons. A single nucleon can be either a proton or a neutron. This notation is commonly used when we're talking about nuclear entities and nuclear material. The X is the symbol for the element, lead, iron, etc. The A is the atomic mass of the material, and the Z is the atomic number. Now, you may or may not remember all the way back to the first quarter, but the Z, that is the atomic number, is what determines the identity of the element. And differences in A between substances that have the same Z is what causes isotopes to be formed. Isotopes are materials that have the same Z but different A's, and therefore they have the same identity but different molecular or atomic weights. Some of these isotopes are naturally radioactive. That is, they naturally undergo spontaneous nuclear reactions. Now, first of all, it's important to take a look at something called nuclear binding energy. And nuclear binding energy is the energy that holds nucleons together. That energy is also called a strong nuclear force. And these are the forces of attraction that hold the nucleus together. Obviously, you have two positively charged protons very close to each other. The law of charges states that these should be repellent to each other, and yet they hold together quite well. Now, the mass deficit or the mass defect is the difference between the calculated mass of a nucleus and the experimentally measured mass of the nucleus. Now, this mass deficit is quite important because this difference represents the energy that's involved in holding that nucleus together. So you have a nucleus that has a slightly smaller mass than the mass of the separate nucleons. So if you take the nucleons and the mass of each nucleon and add it all together, it's going to be slightly greater than the mass of the nucleus as one thing, and therefore that difference represents the binding energy that holds it together. So nuclear binding energy is the energy produced when the atom's nucleons are bound together. This energy also is the energy needed to break the nucleus and into its constituent protons and neutrons. And the mass energy equivalence equation is quite famous. It's the one that Einstein put together, the energy is equal to the mass deficit times the speed of light squared. So when you take the individual nucleons and calculate the sum of those together as a mass, and you subtract the slightly less mass of the nucleus as a whole, the difference is then multiplied, that mass deficit is then multiplied by the square of the speed of light, and you end up with the energy or nuclear binding energy that holds together the nucleus. So let's take a look at a problem that takes this into account. This first problem states that the mass defect for the isotope 206 lead, it says calculate the mass defect for lead 206. The masses of lead 206 is 205.9744 AMU. A proton is 1.00728 AMU, and a neutron is 1.00866 AMU. And then you can use that to calculate the binding energy per nucleon. So let's take a look at how we would do that. First of all, so you have lead 206. Now, the atomic number for lead, we'd have to look up, since I don't remember what it is. The atomic number for lead is 82. So that means if the total weight is 206, then that means we have 124 neutrons and 82 protons. So we take 82 times 1.00728, and we take 124 times 1.00866. 82 times 1.00728 equals 82.59696. 124 times 1.00866 is 125.07384. If we add these two together, we get the 207.67080, and the true mass is 205.97444. So if we subtract these two, we get the deficit, which is 2.69636. So the mass deficit is 2.69636 AMU. And then if we put that in the equation, E equals mc squared, then E is going to equal 2.69636 times C, which is 3 times 10 to the 8th meters per second, and we square that, so that's going to be 9 times 10 to the 16 times this number right here. So that's going to equal 2.4. Let's see how many significant figures we have here. It looks like about 9 of them. Let's see, we've got, let's say 6. So 2.42672 times 10 to the 17th joules. Now that's assuming that an AMU is the same as a kilogram, which is probably not true. So this unit here is probably not right, and I'd have to find how to change that unit. But if you got this answer, that would be good enough for what we're doing right now. Now let's take another one. It says the fusion of the sun is this reaction right here. It says calculate the mass oh, that's per nucleon. Okay, I forgot. This says per nucleon, so we'd have to divide this number. There are a total of 206 nucleons. So we have to divide this number by 206. And so we're going to get 1.17802 times 10 to the 15 per nucleon. And so that's the energy involved per nucleon, which is, depending on what that is, it's quite high. Now let's take a look. It says calculate the mass deficit per nucleon for this reaction. And so we start here and we go over here. So we have hydrogen, which is 1.00728 times 4, because we have 4 of them. And so that's going to be 4.03112 AMU. And we end up on this side with 4.00150 AMU plus 2 electrons, which is 2 times that, which is 0.00110. So if we add that together, we get 4.00260. So that's 4.00260. So the deficit here is going to be 25820 AMU. And per nucleon, again, we have 4 on either side, so we would divide this by 4, so it would be 0.00571 per nucleon. So that's the mass deficit per nucleon for this reaction. Now, when we talk about nuclear stability, what we mean is which of these elements are going to be reactive or non-radioactive, which means they do not spontaneously break down, and which of these are going to spontaneously break down. And the way you look at that is by looking at something called the band of stability, which is shown right here. And a nucleus is stable if it cannot be transformed into another configuration without adding energy from the outside. In other words, it's stable if its current state is at its lowest energy. Now, what this graph does, this graph plots the number of protons on the x-axis and the number of neutrons on the y-axis. And the black straight line represents unity, that is 10 neutrons and 10 protons, 20 neutrons and 20 protons, and so forth. So the slope of the black line is 1. The blue or purplish color is the non-radioactive, and what you see is that as you get heavier and heavier, early on, the non-radioactive elements have about the same number of protons and neutrons, but as you go farther and farther out in terms of mass and number of protons, you see that it gets more and more neutrons compared to the number of protons. And then around that is the radioactive elements, and it can have either less or more protons or neutrons for the number of protons. And when the nuclear reaction occurs, elements tend to travel from the radioactive band to the non-radioactive band. They will continue to react until they reach the non-radioactive part. So this plot shows the nuclides are known to exist and those that are stable. Stable nuclides are indicated in blue and unstable are in the green. Note that all the isotopes of elements with the atomic number greater then 83 are unstable. The solid line is where the slope is 1, that is when n, or the number of neutrons, is equal to z, the number of protons. Radioactivity is when the nucleus or nuclei that are either to the left or to the right of the band of stability. And when they react, they travel toward the band of stability. A magic number is the nuclei with a certain number of nucleons. That magic number is when when that number is reached is when it's stable. The binding energy per nucleon is the total binding energy divided by the number of nucleons. We did that in these previous problems. And this correlates with stability. So as the total energy increases toward the maximum point here, stability increases. So the binding energy per nucleon is largest for nuclei with a mass number of approximately 56. So that's right in here. The binding energy is the highest. And if you're down here and you're heading in this direction, then fusion is occurring. That's one type of nuclear reaction. If you're heading in this direction, then fission is occurring. That's another type of nuclear reaction. Calculate the mass deficit, binding energy, and binding energy per nucleon for the following isotopes: the mass of a proton, the mass of a neutron, and the mass of an electron. And then 1 AMU. Now I gave you the AMU value per kilogram. Now we could use that to go back to our previous problem and calculate those energies in terms of joules. So first of all, let's look at iron 56. Iron 56 has an atomic number of 26, I believe. That's what I'm going to assume. That iron 56 has an atomic number of 26. So we have 56 is the total. There are 26 protons and 30 neutrons and 26 electrons, which means we have 26 times 1.6726231 times 10 to the minus 27 plus 30 times 1.6749286 times 10 to the minus 27 plus 26 times 9.109287 times 10 to the minus 31. So let's look at the total here. So 26 times this number is 43, or 4.3, times 10 to the minus 26 kilograms. And 30 times that number is going to be, let me see if I can do this without using the calculator. It's going to be 18, 1 is 25, and 2, 3 is 8, and 3 times 9 is 27, and 3 times 4 is 12, plus 2 is 14, and it's 21 is 22, and 18 and 2 is 20, and 3 times 1 is 3, plus 2 is 5, excuse me. So that's going to be 4.0 times 10 to the minus, or 5.0 times 10 to the minus 26, plus, and then 26 times 26 times 9.1, etc., times 10 to the minus 31 is going to be 2.368 times 10 to the minus 29. So this right here, if we move this to make it 10 to the minus 26, we're going to have to move it over 3 slots. So that's going to be 1, 2, 3. So that's going to be 0.002368 times 10 to the minus 26. And let me go back and do this and get more numbers here. This will be 4.34882006 times 10 to the minus 26. So if we add all these three up together, we get 9.37597386 times 10 to the minus 26 kilograms. Now, where do you get the other number? Well, you get the other number by multiplying 56 times this number right here. So 1.6605402 times 10 to the minus 27 times 56. And that's going to be 9.29902512 times 10 to the minus 26. So you can see that this number is smaller than this number, so it makes a difference between these two. If we subtract these two, the difference here is going to be 7.694874 times 10 to the minus 28 kilograms. If we did that per nucleon, we'd have to divide this number by 56. And when we do that division, we get 1.3740846 times 10 to the minus 29. So that's per nucleon. And then it says binding energy per nucleon. We take this number and put it in the E equals mc squared formula. So it would be 1.3740846 times 10 to the minus 29 times, and we said that c squared was 9 times 10 to the 8th, or excuse me, 16. So if we do that, we're going to get a number that's about 10 to the minus 12. It will be joules now. It's going to be 1.236676 times 10 to the minus 12 joules per nucleon. This other one is the same situation, and I'm going to let you guys do that.